Karnesh is here today, and he has a pretty broad background. He did his MD PhD training at UCSD, followed by his residency at UCSF, followed by his postdoc at Berkeley, and now he's faculty at UCSF. Um, so, I mean, there's so much to say about Karnesh. I'll just say personally, one of the things that I really appreciate, but also potentially frustrates me, is he did much of his postdoctoral work was on brain-machine interfaces in primates, and he did some amazing work showing that monkeys can learn to control cursors, even from sort of random decoders. So, we spend a lot of time trying to figure out how to design the best decoder. But there's always the question of like how much do we have to match what the brain does versus how much can the animal learn? And Karnesh had this amazing paper showing that over time monkeys can learn, which every time I argue for the importance of we have to know exactly what motor cortex is doing, somebody throws it in my face. But it's wonderful work, and what I really like is that he's brought that perspective of understanding primate motor control now also to rodents, and sees that as a great model system moving forward. So without further ado, here's Karnesh.
Thanks, Chetan, for that introduction. And yeah, so today I'll be talking about some of the work that we've been doing. But I should mention, it's been a pleasure to, it's been fun to visit here, and I've met with some wonderful individuals, and I look forward to meeting others. And it's so today I'll be talking about a systems neuroscience approach to motor recovery, mostly done in rodents, but trying to also do in a small number of human subjects, trying to show that it may be translatable, this general phenomenon. For those who may not be familiar, stroke is extremely common. There's approximately 700,000 strokes per year. It's very expensive in terms of taking care of them and rehabilitation. And importantly, even with the best modern approach, there's still patients, unfortunately, who have impairments, and mainly in the hand and fingers. And that's basically, we spend a lot of time trying to understand, at least in a rodent model, the control of arm and dexterous movements in both healthy and injured animals. And, and partly as a clinician scientist, I think it's important to define kind of what the problem we're interested in. And at this point, interested in trying to augment impaired movements. And so this is a patient, for example, that's part of a collaborative study that I'm part of. It's a typical stroke patient where there's a cortical stroke. And importantly, this patient has a full intact corticospinal tract, meaning the substrate's there. But as you'll see, there's some impairments in terms of getting that intention out into action. So this patient, fully cognitively intact, is only about 40 years old. And this is him trying to pick up an object. And you can see there's a lot of problem with slow, clumsy movement, dysmetric, a lot of dystonia because you can see the fingers get locked into positions. And this is not an uncommon patient that we encounter in clinical practice who would be considered moderately impaired. But for him, for example, he's functionally disabled. He can't work because this is his dominant hand. And the questions that come up are that, often when you think of stroke, there's been a lot of focus on weakness and spasticity. But there are other things that clearly come up. There's slow movements. The movement's extremely variable. There's dystonia, meaning that there's abnormal co-contraction of muscles. And it's known from a lot of work that there's also poor learning in this system. And so what we're very much interested in is trying to understand what may be the circuit basis for that. And in the healthy motor cortex, there's been a lot of great work trying to understand what these systems do. For example, the cerebellar pathways, the thalamic pathways, the basal ganglia, and cortex. And there's proposed ideas for them. And what's unclear is in the setting of a stroke, let's say, how are these same networks being recapitulated during the learning process, during the recovery, and during chronic phases? And so we're hoping to use a rodent model to fully understand how to augment movements using a sort of a network-based analysis. And so that was sort of the overview, and these are the subtopics. I wanted to spend a little bit of time, because I was told it's a fairly broad audience, about the background into neurophysiology of recovery and what are the goals of this line of work. And then I'll show two, at this point unpublished but under review, about the oscillatory network activity during skilled reaching in rodents, and then how this may be used to develop a systems-based approach towards recovery. And so in terms of the background, so what is the ultimate goal, right? So I showed you that patient with these impaired movements, and ultimately we'd love to have this closed loop system, right, which closed loop in the sense at least temporary lock, that if we could imagine that this patient's trying to reach, there must be some neural signatures, and how can we boost that? How can we augment to make those movements normal? And so towards that, what's required, right? What we don't have right now is some cortical biomarker that would say, aha, this is involved in normal learning and movements, and this may be impaired in stroke. So we're very interested in finding cortical, or at least right now, cortical signatures that might predict good or poor recovery, and that may be used to augment the system. In terms of approaches to neural activity, there's obviously, this encompasses almost all of the neuroscience approaches to physiology. There's EEG, there's functional imaging, there's ECOG. I want to just highlight both ECOG and then these single recordings because both will come up. What's interesting about ECOG is that this can be done in patients, and this allows high resolution recordings from the human cortex, and these can actually get into frequencies that are thought to resemble spiking activity. Whereas most of the work I'll show, and I'll show some ECOG, most of it will be the single unit recording, and these are electrodes that go into the cortex and are able to record single action potentials and also field potentials. And these field potentials and ECOG are thought to represent aggregate patterns of activity. And what I'll try to convince you, hopefully, is that understanding recovery at this scale may be useful, that we may be able to find signatures that may be useful in a closed loop system. And this is another view of this from of looking at it in terms of space and time, in the sense that these are the temporal resolutions of different signals, where, as I said, ECOG spikes and LFP tend to be at the millisecond resolution along with EEG, whereas things like MRI and PET are much better at spatial resolution. And of course, there's been work in this domain. There's a really fantastic work of Randy Nudo and colleagues showing that there's motor map plasticity with recovery and training. This was done in non-human primates. There's also a growing body of literature showing that there are changes in neural activations as reflected in the bold signal with recovery. And there's also work this is Leo Cohen's group, showing that there's work, that there's EEG signals of recovery. What we hope to do is extend this work at this resolution with both spatial and temporal scales, just to understand the recovery process and ultimately try to think about signals that could be incorporated into a closed loop system. And then a couple a little bit oddballs, but these are the basis of some of the work, just to point out that there's literature on this. And that's this growing idea of task-related slow oscillation. So this is work that's done in non-human primates, what I've shown here. And it's work suggesting that underlying movement control are these low-frequency oscillatory activity, maybe quasi-oscillatory, because they're not oscillations that start and stop for long periods of time. They may be as brief as 1 or 2 cycles, but they may be important for organizing movements and muscle activity. So here's, for example, from Andrew Jackson's lab and Hall et al. And here's a monkey that's doing a free reach, and you can see the bursts of activity in the EMG. And this is the LFP, again, this aggregate activity. This is the filtered in the low frequencies. And you can hopefully see that there's these bursts of low frequency oscillations as these monkeys are making these movements, which suggests that there's some underlying temporal and spatial dynamics underlying the reach. And that, and these can be also rotational. So not to go too much into this, but basically this principle, I think, has become an important part of what we're looking at with regards to healthy movements and, more importantly, in the recovery period. And the last thing is, you might wonder, well, why might oscillations be important? And at least in our view, that it may be important for muscle dynamics. And so here's, for example, one subject who's making these fast movements. This is from older work, where what they're doing is making really rapid movements from, or at least movements of different velocities from one target to another. And this is the position and the velocity. As they're making slow movements, you can see it's pretty precise with clear endpoints. As they get faster and faster, you can start to see this ringing in the endpoints. And what's interesting is if you look at the muscles, it's kind of well known that with fast, accurate movements, that one solution seems to be that there's this co-activation of flexors and extensors in a very rhythmic way. And this may be one reason why one might see oscillatory activity. As I'll show you, that this seems to be an important part of what we see in our system. As animals are making these rhythmic activities, we see also emergence in the muscles of rhythmicity, suggesting this network-wide phenomenon, which may be important for structuring the timing of actions as well as the limb dynamics that are involved with crisp, fast actions. So hopefully that was enough of a background. And then I wanted to delve into this two topics, which is the, I'm just going to get my phone to make sure I keep time, regarding the healthy and then in the injured, how that framework may be important for understanding recovery. So what we study a lot is this reach to grasp skill in rodents, and we have a fully automated box that allows these animals to train and do this task with no human interactions, which is important for our physiology. And what I'll show you is the work with regards to the role, how M1 and DLS evolved during this task. M1 is primary motor cortex, which is, of course, a key contributor in organizing the spinal cord and muscles likely. And then the dorsolateral striatum, which is the motor part of the striatum, if you will. And this is a key downstream target that's been implicated in learning. And we spend a lot of time recording from these two areas during the process of learning and recovery as a way to understand how our networks being changed over this process of recovery and learning. And one reason to view it as a network is obviously in stroke, you lose large areas, right? So what's plasticity presumably is having at a network level as opposed to, as well as a local level. So it's probably important to understand these interactions. Here's a video of an animal that was one of our better performers after having learned this task. And then the main parameters we look at are the trajectory of the proximal limb. And with learning, they get fairly stereotyped. So the approach, the transport of the limb is fairly stereotyped. They reach and they grasp. And as you can hopefully see that the grasping is fairly complex, right? They're actually sweeping their fingers and doing a nice grasping motion that really emerges with learning. And it's well timed with respect to reach, right? The grasp happens at precisely the right time. And part of what we're exploring is the understanding of the temporal structure of the task, meaning when do they reach, when do they grasp, when do they retract, as well as the aspects of the movement variability in terms of the kinematics, as well as the accuracy, which is how often do they engage the pellet. And so just to show you what might the quasi-oscillatory activity look like with skilled reaching, here's again just the framework of the animal reaching. And these are, in this case, 15 neurons recorded in primary motor cortex. And this is a very traditional PETH, or a peri-event time histogram. And what each line is a single neuron, and then the orange red here represents the firing rate. And you can see that prior to movement, there's about 10% of neurons that are active. And then most of the activity tends to happen after reach onset, and at least temporarily linked to the grasping. And so at least we interpret this, that part of the rodent M1 seems to be involved in the sense of timing. It's active before movement onset of the reach, but mostly the activity can be linked to the grasping. And you might imagine the hand is a much more high degree of freedom, requires a lot more control. And so maybe not surprising that this is essentially the distribution seemingly from a temporal perspective. It gets a little bit more interesting if you look at single trial. So this is a raster of the units as the animals doing the task, and again with the reach, grasp, retract. And here are all the neurons firing. These are just one single trial. And if you look at the population PETH, you get this interesting bursting in groups, right? And we can sort of link these back to the temporal features of reach, grasp, retract. And so it could have been, for example, that really all this is as implied by these mean graphs plots, you might think there's just one sort of a monophasic burst of activity, but really there's, at a single trial level, you see much more of this quasi-oscillatory, meaning bursting. And at the LFP, again, there's maybe one or two cycles, often two cycles that are associated with this reach to grasp task. And there's many, many ways to analyze this, and no matter how you look at it, you can sort of see this level of oscillation. You can quantify the oscillation. And so, for example, here was one analysis. This is in 4 animals across all trials. We looked at which frequency band, which unfortunately looks like the spectrum's gone there, but this is from 0 to 20. So this red is around less than 4 hertz. So which aspect of the LFP signal is the most phase locked to reach onset? It turns out to be this low frequency oscillation, essentially these components. We can also look at the spiking probability relative to this LFP signature, and about 80% of the neurons are highly phase locked to this ongoing low frequency oscillation. We can do spike field coherence, which is looking at how locked on average are these neurons to this frequency band, and they're fairly locked at this around 3.5 hertz. We've also done things that from Chetan's old lab with the Gaussian factor analysis. You can see all of that, the more even complex population dynamics are all recapitulated here. And we chose to just focus on these because these are relatively straightforward ways to analyze the coupling between neurons, LFP, and then, for example, the power itself, the LFP itself. And then, as I said, that we were interested in understanding, is this a local phenomenon or more of a distributed phenomenon? And here's again an animal that's well learned, doing the task after at least 1,000 trials. And here again the raw traces in the LFP and M1 DLS, which is again the dorsolateral striatum, which is this key output from the motor cortex. And you can see that the spiking in M1 at the population level is quite reflected in the LFP, or at least is mirrored there, and similar in the DLS, and again in the EMG. And so we see this network oscillation, and part of what's going on here is that the animal in this well-timed task is doing it quite fast and very precisely in terms of the timing. The reach, grasp, retract tends to be very much locked to these ongoing oscillations, or quasi-oscillations, if you will. And then these are single trial dynamics, again showing that these aren't necessarily cherry-picked, but you see that there's a lot of population dynamics that are essentially locking onto these oscillations, both in M1 and the striatum. And then this is a complex slide. I want to just go through it. So a couple of questions that we were interested in. One is, how does this evolve with learning? So is this just a representation of stereotyped physical actions? Meaning, if I were to take a naive animal and impose structures on them, would you see this? The short answer is no, that this is something that we see emerge. So this is an animal that's doing 600 trials, and this is what the learning looks like. So this is the coding of the accuracy. This is coding of the speed as one measure of the task. And what we see is there's a transition from a slow, inaccurate movement to a fast, accurate movement, which and this is also a consistent movement, consistent with the notion of a skill that's being learned. And if one were to look at this variable period, you can see the timing, and what this is the yellow is is essentially Hilbert transform, or the power in that 1 to 4 hertz band. And so when you see this nice yellow peak here, it suggests there's a nice consistent power. And you can see that as the animal gets well learned and stereotyped, becomes very consistent. The early period, much more variable. And what's striking is the timing of the actions, right? So in the early period, the animal's somehow reaching, touching the pellet, retracting, grasping in a very variable way. And these become quite locked, the transition to very fast skilled action. And again, if we were to look at what I've shown before, is that if you look at the different areas, it really truly seems to emerge here. If we go in and try to match trials in the early period that look exactly the same, we just don't see that. So it doesn't seem to reflect stereotypy. It seems to reflect something that truly emerges, that it's not seemingly a consequence of just doing the behavior itself. And consistent with that, the idea is obviously that this behavior becomes highly locked and highly not very variable towards the end part. And I'll show you some of the work with the lesion work to suggest that these aren't just reflected by the behavior itself, that they truly seem to be an organizing principle for fast, accurate movements. I think, so the other question you might wonder is, we can see these interactions in each area. Are they actually interacting, right? Are they related to the task, or are they related to each other? And so here's the same learning curve. And this is now looking at coherence, which is how phase locked are these two structures. And again, each animal has this interesting transition point when they go from slow accurate to fast accurate. And we see this basically M1 DLS kick in, and that seems to predict this stereotyped activity. And I didn't go into here just to focus more on the stroke, but we can see this pattern in the LFP. We can also look at neurons themselves. And there are neurons that emerge that are truly oscillatory by themselves. So if you look at the autocorrelation of a neuron, it actually has a burst profile as opposed to a more firing, more just a kind of elevation and firing rate, which is more present in the early period, suggesting that there's some, as the animal learns and locks in on a pattern that seems to work, that this is what emerges. Both at the power goes up, the coherence goes up, and I actually, there was a slide that's missing here, and I'll just describe it, is that we have been then trying to understand both the temporary inactivation and the next phase would be the chronic inactivation, meaning stroke, to see how are these different areas contributing. What's interesting is if we put mucimol, which is an agonist for GABA or inhibits an area, if we put an inhibitor into M1, as you might imagine, we lose all behavior. They just don't initiate at all. It gets more interesting if we put an inhibitor into DLS or the striatum. What we instead see is the animal becomes slow and accurate again. So basically the striatum, this coherence, seems to be important about making these actions fast and accurate, but not necessarily accurate. And I should have put a slide in there, but and what we'd also lose is the quasi-oscillatory activity, which to us suggests that there's a network interplay between M1 and DLS, which is about this transition from slow accurate to fast accurate. And so this is our working model that hopefully will help you think about the stroke, the subsequent section on the stroke, which is that our working hypothesis is that an unskilled task, it's just very variable. There's no set pattern. The animal's essentially exploring the space and the task parameters. So we get a lot of firing that's essentially not oscillatory. Field potentials of low power, not very oscillatory. There's a lot of variability. As a skill emerges, becomes fast, accurate, and consistent, at least in a correlational sense, we find that what seems to emerge is this bursting phasic activity in M1 as well as in striatum that's also reflected in the field potential as well as in the EMG. So there seems to be something about this quasi-oscillatory pattern that's important for timing and accuracy and consistency. So I don't know if there are any questions or before I move on to the next. All right, great. So the next phase would be, so at least when we move to the stroke work, we had an operational hypothesis that there may be something about this oscillatory patterns that's important for the recovery process. And then the question is, can we then modulate that to improve recovery? And that's essentially the subsequent sections, is to show that this oscillatory activity seems to be important for those animals that recover, is not recapitulated without recovery, and that by modulating it, we can actually make things better. And so just to give you a sense of what does a stroke look like, or at least what's the behavioral consequence of a stroke, we use two stroke models. One is a focal M1 stroke, which for us is much more controlled, so we can make a lesion and put electrodes around it in a very precise way. The other is more of a clinically relevant model, which is the MC occlusion, which is harder to predict where the lesion is, but is more considered more translational because it's more involving the vasculature, as opposed to this, which is more of a photothrombotic lesion. And so this, for example, is a typical animal with good recovery. They usually recover over 2 weeks to 4 weeks, so about a 28-day period. And this is what an animal looked like around this midpoint. And the important point is that they really seem to be okay with the reaching, but they have a hard time grasping and coordinating the grasp. The grasp, they sometimes grasp early, they grasp late, and even if they grasp, they have a hard time picking up the pellet. So it's a statement that's all about distal function. And that you can see that even after a stroke, that they quickly are able to recapitulate their proximal movement, suggesting this, which is known in the field about the distinction between cortical control of distal function versus more proximal function. And so, so how do we do the electrophysiology? How do we measure the electrophysiology of sleep? Of stroke. Sorry, that's other. So we do these two. We have been using two types of models, as I mentioned. One is the MC occlusion, and what we do here is this is a vascular occlusion in which, and the interesting property of this model is that you could put in arrays, capture the pre-stroke baseline, and then induce a stroke, and in the same animals, look at the same arrays, so you have a sense of what was the pre-baseline activity and the post-baseline activity. So what we do is implant arrays, and this is the middle cerebral artery is the major artery that's supplying the lateral aspect of the brain, and we induce an occlusion of that, and then we can look at the recovery. The other model that I mentioned is a photothrombotic stroke, which is a much more focal cortical stroke. And this allows us, and because we know exactly where we shine our light, and it's basically triggering a photocoagulation reaction, that we can very precisely induce strokes and put electrodes a priori in the perilesional cortex. So this ends up being much more scientifically tractable. This ends up being more translation. As I'll show you, we find the same phenomenon in both. So, but it helps at least support the notion that this may be generalizable finding. So here's a example of an animal pre and post stroke using this MC occlusion model. And so this animal was well trained. So usually we do at least like 1,500 trials, and we can measure this precisely in our automated box. And we have criteria in which they must meet at least 75% accuracy consistently. This was the animal that was kind of cruising along, doing well. And here's again that plot of the movement times. In this case, it's reach onset is the dotted line. The black dots are the retraction period. And you can see this power in the 1 to 4 hertz again shown here. And this is about 1 week post-stroke. And so the animals are now able to reach. So they're actually making the reaches. And what you might see here is there's a lot more variability now in when they're at least retracting here, but you can infer that the attempts at grasping were much more variable. So just way more variability in the system. And what we consistently find is that there's loss of the low frequency activity. And you might wonder, well, are these just neurons that are just, is that dead tissue? And so the way we define tissue that's still viable is that all these electrodes that we analyze have actually, we can record neurons on them units, right? So when we put a wire into this area, in the MCA model especially, we often end up recording adjacent to the stroke, so not in the stroke itself. So all our electrodes are actually picking up neurons, so the vast majority. And so we know that these are viable neurons, and that there's not, and we lose this low frequency oscillation. And here's a quantification across these 4 animals, where there's quite a dramatic drop in this 1.5 to 4 hertz power, the so-called LFO, which is at least suggestive that this may be somehow important in this reach to grasp task, because the reaches here tend to be fairly normal. And here's another view of that, which is looking at units as well as the PETH. And so, we can certainly record neurons in this area, and they seem to be well modulated, but they don't have that phasic component in them. So they lose the phasic oscillation that we hopefully have been used to seeing with respect to the reach, grasp, and retract. And so this is just a statement that in those MCA models in the acute period, as animals has really dramatic drop in accuracy, the animals are reaching, there's neurons that are firing, but they don't have this phasic oscillation. And so then the next question is, okay, that's in the hyperacute period. Now what happens as we follow these animals with recovery? And in this case, these are 8 animals that we just analyzed over the first 10 days. There's a lot of variability in recovery, but it's just looking at the not just the acute period, but then the recovery over time. And so here's an example of one animal that was had a stroke again and had a good recovery in this case. So this recording was started day 5 post-stroke, and then each day the animal had these rehab sessions. And what's striking, at least in this animal, was there's a transition. I guess this would be around 2 weeks post-stroke, where for this animal, it just switched into being unable to grasp. This is all, and just to point out that they're definitely making the reach, because these tell you that they're touching the pellet, knocking it off, and retracting. And that when they switch, it becomes, this power comes on, and they become much more accurate. And so we interpret this, partly what we see is a much more functional grasp, because now they're able to grasp at a right time and able to retract the pellet. And and if we were to look at across all animals, if you look at the low power, so if you look at sessions 1 and 2, there's really this weak power in this 1.5 to 4 hertz, whereas in these later animals, let's say I believe it's on day 10 here, on average is much more increase in the power. And this is just a quantification across multiple animals. This is just a heat map with frequency here and then time here. And this again is mostly limited to that pre-reach period, right? And this looks much more brief because we're averaging so many trials. So this is just the mean power. If you were to look at each individual animal's single trials, this is obviously lasts a lot longer. And this is an example of the temporal dynamics across late versus early, which is again an increase in power. And just to make the point that these aren't just localized phenomenon, there's actually a network-wide, meaning in the perilesional cortex. This is what early looks like. No matter these are, for example, 16 channels that are contiguous. We don't see much of this power. As animals recover in the late period, you just see this these yellow bursts, which suggest that there's this increase in low-frequency oscillatory power. And then lastly, the question is, how well does this predict the recovery process? And so what we're showing here is the changes in the power, and we z-score it here only because each animal's absolute amplitude may vary depending on the impedance of the electrodes or whatnot, but we z-score relative to the baseline period. And that if you look at trial-by-trial recovery across these 8 animals, that the recovery of this low-frequency power is an important predictor of the change in success, right? So this suggests that as animals are continuing to rehab and get better, that we're able to predict some of the variability a significant variability in the change in the success rate over time. Right. And so, it's important to also show that the spiking goes along with LFP, partly because with LFP, we're not exactly sure where that comes from. It's still, there's a lot of ongoing work regarding what exactly is the source of LFP. So in all of our work, we try to make sure we also record locally from single neurons, because we know that these are neurons that are local, that they're, an action potential is an action potential that comes from 100 micron, a likely 100 micron piece of volume. And so this is just an example of what the recovery looks like, that this was a stroke animal that had recovered. And so that same animal, in fact, and then all of a sudden, you start to see this oscillatory bursting as well as the oscillations in LFP. And this is now looking at across multiple animals, what do the mean peri-event time histograms look like, meaning the spiking around reach onset. And you can see early on, they're much more variable, and the tiling, if you will, meaning how well they're stacked, is much more broad and distributed and kind of fairly weak. And they become much more locked, consistent with the idea that they're just much more organized at a mean level, which likely reflects this organization in the LFO here. And this is, again, a measure of how well are single neurons, neuron by neuron, locked to these ongoing oscillations. So it's a measure of the phase consistency between spiking and then the ongoing oscillations. And so early on, most of these neurons, these are viable neurons, they're firing, but they don't seem to be organized by this low-frequency oscillation, whereas late in recovery, on average across multiple animals, there's this around a 3 hertz peak, which again suggests that these neurons are nicely phase locked to the ongoing low-frequency oscillations. Right, so hopefully that indicated that in the healthy animals, we see this oscillatory activity that emerges with learning. In the stroke animals, with recovery, we see a general recapitulation of the same phenomenon in the perilesional cortex. The remaining couple areas I wanted to highlight was, one, is this at all relevant to human stroke subjects? And so I'll show you some evidence in that regard. And lastly, can we modulate this ongoing activity to make animals reach better, right? So as a way of ultimately moving towards this closed loop system that might be able to use this biomarker as a way to improve function. And this is, again, for those who may not be quite as familiar with all this, but so this are the different approaches to recording. And so what I've been showing you mostly so far is recordings from arrays that are actually implanted in the cortex. So this allows us to record single action potentials and then the field potential, the LFP. ECOG is a nice intermediate between surface EEG, which is recorded from the scalp, and these more invasive approaches that actually penetrate the cortex. So this is a disc that's sitting on the subdural space. And this has become an important tool to record in human subjects, and specifically in subjects undergoing epilepsy. And so we have a collaboration with a colleague of mine, Dr. Edward Chang, who's a neurosurgeon, who's really doing some pioneering work with ECOG and language mapping and understanding human dynamics. And we happen to have a subject that, for him, he mainly records from epilepsy patients, and then rarely he has, unfortunately, someone who has a stroke and has epilepsy. So we get an opportunity, this is for purely clinical reasons, to record from someone's cortical surface who've had a stroke. So this individual was actually in the late 30s, unfortunately, then had a stroke, then developed epilepsy later. And he's an interesting candidate from just understanding stroke, is that his also corticospinal tract was fully intact. So his substrate's there, but we're able to essentially gather cortical signals from him. And so what he, and this is with consent from the CHR and the Institutional Review Board. And so what happens is that these patients undergo surgery to localize where their seizures are coming from. And they're sitting in a hospital room, and they often consent to do motor tasks or learning tasks as a way to contribute to the broader scientific literature. And so in this case, this subject was able to do center out movements for us. And this is not quite the reach to grasp in the rodents, but still trying to make fast, accurate movements using the proximal arm. And here's a power spectrum from a typical channel in that subject. What's striking is that you see this high frequency activation here, which is considered high gamma, and there's a lot of literature suggesting that this represents local spiking. You probably see this giant hole there, that blue there, which suggests that he doesn't have much of this low frequency oscillation. And that's essentially one of the findings that we noted in him. And keep in mind that he's someone who had a stroke, and at the time of this monitoring, it was 4 years post his deficit, and he, living in the Bay Area, had pretty phenomenal therapy, and he was maxed out on his therapeutic in terms of physical therapy and rehab. And so even in this chronic phase, he was able to do movements, but not well. And in that setting, again, we didn't see this low frequency oscillation, and this high gamma was kind of quite distributed. All the yellow dots here represent where we see local spiking. And so you might wonder, well, could this be just some oddity of this person? And so what we did was compare him to 2 intact subjects. So in this case, all three are being monitored for epilepsy. And so they all have intractable seizures, but they all have very similar motor, they have grids over sensory motor cortex. And what's striking is if you look at the 2 quote unquote intact subjects, because they're actually able to make normal movements, we consistently saw this low frequency oscillation. And if you look at, for example, the rats, very similar, right? The power spectrum of their movement potentials look very similar for the intact versus those that are recovered. And the stroke subject, even the 4 years out with impaired movements, had this impaired low frequency oscillation. And here's a spatiotemporal view of that. So these are the entire grid just made into an image. And what it's showing is like the waves of the low frequencies during the task. So this is T1 would be pre-movement, T2 would be at time 0, T3 would be after. And so in both of these quote unquote intact subjects, at least motorically intact, we saw these waves of low frequency oscillations that would be triggered by the movement, that would also phase lock with the high gamma signals, but that entire organization was absent. And so again, with the fact that the high gamma was present would imply that these are a viable tissue, there's local spiking going on, but they aren't able to organize these movements. And so at least in a correlative sense, it's a potential validation in a small group, and to be determined if it'll generalize, but suggestive that this oscillatory pattern may be important in multiple species. So the last thing I wanted to end with is just to close the loop, so to speak, is can we interact with this ongoing oscillations and make things better, right? As a way of starting to be more causal about this and not just correlative. And I'll tell you, we spent a lot of time trying different electrical fields. This is all at this point done with electrical fields. And so we started with both anesthesia as well as reaching animals to understand what's the right electric field that would best interact. And this ends up being the one we settled on, which is that we put in cranial screws, which are very low impedance. Unlike the recording arrays, these are fairly large, so it's easy to pass current without inducing large voltages. And they're before and after the stroke, and our reference or ground is on the other hemisphere. It turns out, and this is maybe consistent with the human TDCS literature, there's something about creating large fields that are important. We don't see this if we use local references or references in the same hemisphere. So this is very much of an engineering approach, but this, at least empirically, was what we found was effective. And our hope was, can we try to find patterns and parameters that would make a chronically impaired stroke subject, stroke animal better, right? So our hope would be, can we induce temporary lock stimulation to improve the limb positioning and the patterning and the behavior? And so, it gets really hard to record and stimulate at the same time. And so what I'm going to try and show you is that it's easier to do this in anesthesia because you have really good recordings there because you can move your electrodes. And so my claim here is that the same type of stimuli may result in similar things in anesthesia and in stroke. And so this is an anesthetized animal where you can see it's, and you may or may not know this, but in anesthesia, in ketamine anesthesia, you get this low frequency oscillation around 3 hertz. And so it's a potential model, and that's how, in our mind, we developed our parameters in anesthesia, and now, as I'll show you, validate to the awake behaving. So it gives us a test bed to try to optimize our parameters. And so we can record neurons in anesthesia. When we stimulate, you can hopefully see that they become much more phase locked. And so we can, by this stimulation, and what we're doing is right now a direct current stimulation, just a pulse up, down, and then after the reach, we do a charge balancing. And then, so we can increase the power as well as the spike field coupling, right? So by inducing these brief pulses, these are several seconds long, we can induce locking, and then when we turn it off, it goes back to baseline. So this gives us a way of, and then the important point I think was that we found that this method was effective in anesthesia. Then we did this in awake, and so in the awake, it's much harder to record neurons as well as field potentials. But we can at least say that this is in the awake behaving stroke animals, when we induce the same current, we can actually increase this oscillation as measured in the LFO, in the low frequency, in the LFP. So we don't have the spikes, but at least it's concordant with this finding where the power does go up, and we can see that the task evoked power at the time of reach can go up. And this is a quantification of 4 animals. So it's fairly robust. And the amount of current, just to point that out, is on the order of 100 to 200 microamps. So it's fairly small. These, given how high our impedances are, these are generally, we'd consider them sub-threshold. For example, here, it's not like we see a dramatic changing in firing rates. It's more of the, based on our work, our hypothesis that they're much more of a sub-threshold depolarization. So this is just to show that using this type of activity, or electrical stimulation, we can change the patterning of activity. So the big question is, does this affect behavior? And so this is one example of an animal in which we can use the same montage as, I guess this case was 200 microamps. And so we have an animal, and all the data I'll show you are animals that are 1 month post-stroke. So they're in the chronic phase, right? So they're in the rodent models, about a month, they don't tend to get better with spontaneous recovery. So you can keep rehabbing them, they're plateaued. And so here's an animal where we turn on our device system, and this is 25 trials, and you can see an improvement around 60%. When we turn it off, they go back down. And so what we have generally found, it's this on-demand improvement. It doesn't tend to generalize. So it's a sense that in this chronic state, when we give these temporally precise stimulations, they improve. If we turn it off, they go back to baseline. So this is our pilot data to show, can we do this or not? And then the next phase, what we tried to do was say, okay, can we do more of almost like a clinical trial, right? To take 2 groups of animals and do this in a consistent way and understand, is this consistently better in 2 different stroke models? And this is what we did, was we're not quite there to make this fully closed loop. We're working on that. Right now, it's responsive in the sense that we turn on the pulse right when the door opens. And so our animals are so well trained that they generally reach right when the doors open. And so the moment they can reach, they do reach. There's some jitter, so it's not quite precise yet. I'll show you the precise version next. And so here, all we're doing is turning on a pulse 500 milliseconds before the door opens, the animal reaches, and we're comparing 3 conditions: no stimulation, stimulation, and a sham. So what we do is just turn on this pulse for a very brief period, which we have found is not effective. And this basically controls for any alert. You might imagine that a little, brief pulse may make the animal more they may be better because they know to expect the stimulation. So it's a control for that. And this is what we found in this case with 7 animals and multiple sessions. And what we're doing is for each daily session, we're comparing sham and stimulation to the no condition. And so it's normalized for each day. And at least for most animals, whether it's MC animal or thrombotic stroke, these animals were significantly better in terms of accuracy. We've now gone back and looked at the kinematics. It's a little bit harder to tell, but they tend to get faster. So with the stimulation, it's harder to tell with the variability, but they're certainly faster, and the accuracy is the most dramatic in these cases. So the last experiment here I wanted to just point out was that the previous one wasn't really timed, wasn't precisely timed to the reach, right? It was more broadly timed because the door opens, the animal would reach, and there's some jitter of at least 100 milliseconds or two. So the next set of experiments, this is moving closer towards what might a closed loop system look like, is to understand if we could give a much more precise pulse, does that matter? And so what we did now in 4 different animals where, again, in the chronic state, we would give these 1 second pulses. So 1 second is about the duration of their preparation and the reach period. And what we are varying is the delta t, which is the time between when the pulse started and when they actually reach. And so a negative delta t would be the pulse started before reach, and a positive would be after reach. And it's trying to understand, if we just each animal, so each of the 4 animals got about 1,000 reaches, and we just randomly pulse. So they always got a pulse, but we varied the timing. And we got this potentially quite interesting relationship in which the red curve here is the net improvement across animals, across sessions, relative to the delta t, right? So negative 0.05 would imply that a pulse started about 500 milliseconds before the reach. And interestingly, this was the most effective, and you might have predicted this, but it was a nice validation. And then the black line is the low frequency oscillation, right? So this is the mean LFP across all animals we've ever recorded from. And so you get a sense that there's certainly this quasi-oscillatory, which starts often around 500 milliseconds before the reach and has a couple of cycles, time 0 being the reach onset. And so we see this nice relationship where we get a really significant improvement if they're right before the reach onset around this period. We're not quite powered to make claims here just because if you do multiple comparisons and all that, these survive multiple comparisons like with Bonferroni or cluster correction. These don't. But at least there's a potentially interesting relationship that all animals show, which is a slight worsening if it's at this phase, and again a slight improvement at this phase, suggesting that there may be some temporal structure which potentially validates the need to be more closed loop, right, to be more responsive. And this is an ongoing work that we're looking at, is trying to create a fully, if you will, ultimately autonomous system that would try to detect a reach is about to happen, specifically a reach to grasp, but not that all reaches, and trying to stimulate much more to entrain these pulses, right? And that's our next line of investigation. So this is our working model that the intact animal has this quasi-oscillatory activity that also seems to be about patterning the spiking, and this may underlie this fast, accurate, and consistent movements. What we see in the injured animal is a reduction in both the power as well as the oscillatory spiking in the perilesional cortex. And what we hope to continue to show is that this temporally precise direct current stimulation is actually able to reinstantiate this. And I will mention that for those who are aficionados of currents, direct current isn't great for the brain. And so another way that we've been having success is also by using alternating current, which is much easier to charge balance on a moment-by-moment basis. And that's proven to be equally effective. And so I think moving forward, that's another part of whether this has to be direct current, meaning a step, or something more complex from a charge balance perspective. Those are things we're also working on. So that's the last bit. And so I just wanted to thank the folks who actually did this. The healthy reaching work was mainly done by Stefan Lemke, a graduate student in the lab. And then the stroke work was quite a lot of work, including the human work, and about 50 animals. And that was a combined work with Dakshin, Ling Guo, and Tanuj. Dakshin and Tanuj are postdocs in the lab, and Ling is a graduate student. And so we're excited about trying to move forward with that. And then I want to thank the funding sources. Thank you.
That was really well done. Really amazing work.
Thank you.
I found it really exciting. Happy to open up we have about 10 minutes for questions.
So I was curious if you thought these oscillations were primarily important for
Right. No, I mean, great question. So the 300, 3 hertz would imply a cycle of about 250 to 300 milliseconds, and certainly a lot of processors can be engaged in that, including sensory feedback. So short answer, we don't know. But one suspects that there may be 2 things as part of it. Is that certainly there's M1 activity that's propagating down to dorsolateral striatum within about 10 to 20 millisecond, or maybe 10 milliseconds is one synapse, and then the muscle activity is about maybe 50 milliseconds. So certainly you could account for purely feed forward from M1 to muscle 50 to 100 milliseconds. Almost certainly in that clock cycle, then there's going to be feedback, and so I guess I wouldn't be shocked at all if that. And one I think hypothesis of those who think about these LFOs is that part of what the LFO is doing is maybe chunking activity both to take into feed forward and feedback. And in this task, these animals do require not work we have done, but Johan Wishaw's lab has done things like deafferenting the limb, and these animals have a hard time. And so even in this stereotype way, they seem to still need sensation, certainly with the interaction part of it. And so long answer to say I would almost predict, but we don't know for sure yet. Yeah. Yeah. Sure.
If I understood that last part, there were some cases we stimulated after the reach already began.
Yeah.
Can you say what you think is going on there? So were those just qualitatively similar as stimulating prior to reach beginning?
Right. So I think we're not powered necessarily to look at that, but the timing of that tends to be when the grasp happens, and so in the timing of the task, there's the reach, grasp, retract, and so the second phase seems to be when they're actually interacting with the pellet.
I see. So as long as the stimulation
Yes.
comes along in time for that part.
Yes, that's our leading hypothesis, and that's where I think knowing the structure of the task can matter. And I was talking with I think Mike. You could imagine having in a much more sequenced task, you may have many more times to interact with the task, as opposed to, and then the reach to grasp is I find very interesting because there's this, there's the arm part which has potentially its own control system. We were talking about this, and the grasping seems to be very different, and that so part of learning the task is the timing of when to grasp, then actually doing the grasp, and those can become dissociated when we do, for example, basoganglia lesions, that the timing's off, but then they grasp, and so I think. Those are things that we're trying to think of ways to do that without getting super underpowered, is trying to tease apart timing from action. And there may be ways to do that in different sets of animals. Yeah, but that's a short answer for that. Yeah. Or the long answer for it. Yeah. Yes.
Can you observe the oscillations from EEG as well?
Yeah, actually, yeah, good. So I think we don't do that, but I think I've talked about this to the Leo Cohen's lab and at the NIH, and they are, there's a postdoc there who was actually looking at EEG in acute versus, and so yes, and I don't want to speak for their results, but it may be promising. The other that's older is the work of Niels Burmauer with SCPs, subcortical potentials. So those are not so much looking at frequency-based, but more these DC potentials, and there may be some concordance with that. It's hard to necessarily relate back to, because we don't know where the generators are or where the sources are, but there's some work in that regard to suggest possible concordance, yeah. And then I think the one comment which I think if you're talking to EEG folks, and I've asked even our local people at UCSF to try and, is that there's concern about movement artifacts with EEG, especially the low frequencies. And so I think in our mind, we've spent a lot of time making sure everything we see in our field potentials, we see in spikes. Because with action potentials, you don't get artifacts just because the spike waveform is pretty invariant. That's number one. We also look at our stroke animals for making lots of movements. We don't see, and so I think whereas it's a little bit harder to convince EEGers to care about that low frequency, because they worry about all those things, which are, but yeah. Yeah, sorry.
Very nice talk.
Thank you.
For the presentation. I have a question, kind of in line with what Garrett was asking. When you have these TBCS stimulation before the reaching task, that reaching task right now, from what I understand, is still queued, right? Basically,
Yes, it is queued. Yes.
Basically, the gate opening and then
Yeah.
at
Yeah.
initiated by the animal itself, and if you can comment on if that actually proves to be having a positive effect, how do you envision this paradigm to be translated for a clinical application?
No, very good question. And so the way we have tried to look at that is that we have trials that the animal just doesn't react quickly; they're distracted, so the gate opens and they reach a lot longer, and so those we see the same thing. So if we just look at reach onset, that seems to be a relevant feature rather than the cue. So at least we have, I haven't shown this here, but we can analyze data where the animal, let's say a well-learned animal, let's say it was just distracted, the door opened, and they reach much later, that we'd see the exact same relation. So it doesn't seem to be linked to the cue itself, but the reach onset. It's like the reach, grasp, retract. And so that's number one. And number two, yeah.
Then your delta is still with respect to the cue or with respect to the reaching?
The reaching, to the reaching. So we readjust. So when we do readjust for the reach onset. Excellent point, right. So the delta t is relative. So we're giving these pulses, and we're just randomly distributing them because right now we don't. When we did this, we didn't have a clear way to measure the reach onset and deliver this before reach, and so we just randomly dispersed the pulses, and then we would bin them based on the delta t, based on going back, looking at the kinematics, when did they exactly reach, and so it's a very good point. It's not delta t relative to reach, but not q. So. Absolutely, good point. No. Right. And so I think there's two approaches. One is that we've been trying AC stimulation, and so that there may be a DBS-like approach there, just always on. That's number one, and we're trying to understand that. The second is that we've been so for example, could you do a closed loop system just based on the LFO, which tends to be somewhat noisy. And so the way that we have been implementing it, which is based on EMG, it's like a gate system that looks at EMG and the signature. And so it turns out there's some simple logic that would reduce the false positive dramatically, that if an animal were to reach the grasp, if we had measurements in a couple of EMGs, and our operating hypothesis is really about timing the grasp features. So part of doing well, our hypothesis is that they're reaching okay always. It's just the timing consistency and timing of when they grasp and how they grasp. And so if we could just, and so for example, potentially we could exploit the second pulse. That's another one. The other, and this is something we're still ongoing work, but we can, when you try to reach the grasp, there's predictive signals in the really proximal muscle. So before they reach, you can actually see activity in the deltoids and the pecs, which imply that they're going to reach. That's number one. If you were to couple that with the LFO, that reduces each signal by itself is not that predictive. When put together, it narrows it dramatically. So that's maybe one. That's potentially the most translational to have, because we know that even in clinical stroke, the proximal muscle is just vast in the moderate disability patients, not in severe, that their proximal tends to be okay. And those muscle patterns are not normal, but they're nice bursts of activity. So I think some version of that, and that's like we've tried this where we're still working, trying to come up with that logic, but I think that's probably the most translatable. Alternative, like I said, that I haven't presented this here, but the AC is definitely safer for the brain. The DC would, because it's charge unbalanced, you worry about charge buildup and issues with there, so you have to worry about discharging. With AC, it's inherently charge balance, and so that's something we're still testing right now. And so, and just partly we have put that on pause because if one worked, then you don't have to worry about the precise timing. And the important feature there is with the AC is that amplitude matters because these are weakly coupled. If the current were too high, it would actually, the animals don't reach. Actually, it's kind of interesting. It almost inhibits reaching if you overdrive the system. And so it's finding, so there's some optimization there. So we're trying to understand that space before diving too much into this autonomous. But that's, hopefully we'll know that in the next few months. And then, yeah. I hope that answered the question. Yeah.
Everybody, let's take a second to thank our speaker for